Now we will solve for the eigenvalues and eigenvectors of the Hamiltonian of the harmonic oscillator using a completely different method, which is an algebraic method. So unlike in the last section where we use the methods of analysis, namely thinking of a differential equation and its solutions, in the algebraic method one focuses on the fact that you have a linear operator which itself is made up of smaller, not smaller, but more fundamental linear operators, the position and the momentum, and that the properties of the Hamiltonian are to a considerable extent determined by the fact that the underlying fundamental linear operators have to have certain algebraic properties, specifically that they have a certain commutation relation. So the Hamiltonian is this quadratic form in position and momentum, right? And the commutation relation, which we will use, says that the commutator of x and p, which is to say the difference between acting with x and p in one order and the other, is proportional to the identity operator with a constant which is I times Planck's constant. The commutator by definition has to vanish if you use the same operator in both slots, so it doesn't matter which order you multiply them in because they are literally identical. So the commutator of x and p must be 0. So in the algebraic approach we are going to say we need to find the spectrum of H, its eigenvalues, its eigenvectors, expectation values of various functions of x and p in the eigenvectors of H, but we will do so by focusing on these algebraic aspects, while of course keeping in mind that x and p are linear operators in some vector or Hilbert space, but we will not specify, unlike in the analysis approach, which Hilbert space they live in. So we won't focus on the fact that these are square integrable functions of on a line. Discuss where this commutation relation comes from. In a purely algebraic approach to quantum mechanics, which is historically associated with the name of Heisenberg, who invented matrix mechanics, you would pretty much postulate this as something fundamental. Indeed, it was noticed by Dirac that in classical mechanics, in the Hamiltonian formulation, you have an object called the Poisson bracket, which some of you may have come across, and in classical mechanics the Poisson bracket of x and p is 1, and that translates in quantum mechanics to the statement that the commutator of x and p is 1 up to IH bar, where 1 now has the meaning of an identity operator in the requisite vector space. But what we can do is to simply check that this commutator is completely consistent with and indeed implied by our previous definitions for x and p when they act on wave functions in our favorite Hilbert space. So here goes. We act with the commutator of x and p on some function psi of x. So we act first with p and then with x, and then we subtract from it the opposite action where we act first with x and then with p. In the second action there is an extra term in which d dx acts on x, which survives when we take the difference, and that gives us the next line, which is IH bar times psi of x. So in this fashion we see that acting with the commutator of x and p is equivalent to taking the function psi and simply multiplying it by I times h bar, which is to say that the commutator is equivalent to IH bar times the identity operator. To proceed further, we are going to define two new operators, which Griffiths calls a plus and a minus, which are linear combinations of x and p, as shown here. More conventionally, a minus is referred to as a and is called the annihilation operator, and a plus is written as a dagger because you can check that a plus really is the Hermitian conjugate of a. It changes the minus I into plus I, and x and p being Hermitian leaves everything else unchanged. And a dagger or a plus is conventionally called the creation operator, for reasons that will become clear a little later. Now you might ask why we want to define these operators, why are they natural? And one way to see that is to cut through the clutter a little bit by setting all constants in the Hamiltonian, such as the mass and frequency, to 1, so that the resulting simplified form looks just like a quadratic form, where I've however chosen to keep the factor of 1/2 in front. Now, if this was a classical function, or an ordinary function, I could simply factorize p squared plus x squared into x minus ip times x plus ip, and now I've stuck in the root 2's in appropriate places. So one sees that the simplified form of the Hamiltonian is simply a plus times a minus. And now, in writing this identity, we used the fact that this product, x times x, reproduced my x squared, minus ip times ip, reproduced the p squared, and that the cross terms cancelled because it didn't matter whether I had an x from here or an x from there and a p from the other place. Now, you'll spot immediately that in the quantum setting, where these are operators that don't commute, their order does matter. X times ip and minus ip times x are not going to fully cancel. In fact, if you use the commutator, you will find that there is a leftover answer. So, in the quantum mechanical problem, this identity is going to be modified some. And in the next line, I've written down the modified version, where I have not only taken account of this non-commutativity, but I've also restored all the units that I had dropped in the line above. And the net result is this identity, which says that a plus a minus, quantum mechanically or as an operator product, is equal to 1 over h bar omega times the Hamiltonian minus a half, which in turn can be used to write the Hamiltonian, as I've done in the line below, as h bar omega times the combination a plus a minus plus a half. So that plus a half came from this non-commuting character of a plus and a minus. So we need to quantify that non-commuting aspect, and we can do that by simply calculating the commutator of a minus and a plus, given that we know the commutator of x and p, and a minus and a plus are simply linear combinations of x and p. When you do that, you get a very nice answer. The commutator of a minus and a plus is simply 1. 2. Okay, now to the spectrum of H. Now notice that in H, the non-trivial bit is the combination a plus a minus, the product a plus a minus, because the 1/2 is just a constant and h bar omega is just a multiplicative constant. So if I knew the spectrum of a plus a minus, if I knew its eigenvectors and its eigenvalues, then its eigenvectors would be the eigenvectors of H, and the eigenvalues of H would be just given as h bar omega times 1/2 plus the eigenvalue of a plus a minus. So a plus a minus we're going to call n, and it's generally called the number operator for reasons that will become also clear. And in the algebraic approach, we start by saying, let's imagine it has one eigenvector with an eigenvalue lambda. So we're not saying what lambda is, but we assume that there exists at least one eigenvector. So this is then the statement, that there exists an eigenvector which we're also labeling by lambda with eigenvalue lambda. What we will show next is that from this eigenvector we can construct another eigenvector with a larger eigenvalue, specifically with eigenvalue lambda plus 1. This we do by acting with a plus on lambda, which gives us the relevant eigenvector. And from the eigenvector lambda we can also construct another eigenvector with a smaller eigenvalue, namely lambda minus 1, by acting with a minus on the eigenvector with eigenvalue lambda. So in this fashion, a plus and a minus will be what are called ladder operators or spectrum generating operators. Given one eigenvector with an eigenvalue, it will give us other eigenvectors with eigenvalues which are either larger or smaller. The way we show that is by simply acting on the state, say a plus lambda, with the number operator. So if I write it out, the number operator is a plus times a minus, and then it acts on a plus acting on lambda. Now we are going to assume that the operators are such that their multiplication is associative. That seems utterly natural if we're thinking of them as generalizations of matrices. Since they're associative, I can change the order of multiplication, decide to first multiply a minus and a plus, or act with a minus and a plus on lambda, leaving the action of a plus, the leftmost a plus, for later. Now, the a minus a plus product can be transformed via the commutation relation to 1 plus a plus a minus. I can shuffle that order. So, in other words, move one past the other, but in the process I pick up a constant. And so I end up with what I have here, which is a plus acting on 1 plus a minus acting on lambda. Now, a plus a minus is just a number operator. So the term in brackets acting on lambda picks up 1 plus lambda and returns the state lambda, leaving my a plus sitting to the left, but the a plus then commutes with 1 plus lambda, which is just a number, or a number times the identity. And so altogether, the number operator acting on a plus times lambda ends up returning the eigenvalue lambda plus 1, multiplying the starting vector, which is a plus acting on lambda. So I've discovered that a plus acting on lambda is an eigenvector of the number operator with eigenvalue lambda plus 1. Likewise, we can show that the number operator acting on a minus lambda will return lambda minus 1, and therefore a minus acting on lambda is an eigenvector of the number operator with eigenvalue lambda minus 1. So this is very nice. I started with an eigenvalue lambda, and I have seen how to construct an eigenvalue lambda plus 1 and the corresponding eigenvector, and likewise the eigenvalue lambda minus 1 and the corresponding eigenvector. And obviously I can repeat this process, go up the ladder or down the ladder, in order to get all different eigenvalues separated from lambda by integer units. Now, in this fashion it may look like I have an infinite number of eigenvalues lying above lambda, as well as an infinite number of eigenvalues lying below lambda, but this in fact can't be the case. The reason is that a plus a minus, which is a dagger a, which is in the other notation I suggested, or the dagger of a minus multiplying a minus, is a positive operator. A positive operator is one whose expectation value in any vector or any state is positive. Another definition is that all its eigenvalues have to be positive. So let's use the first definition. We will take a general vector psi and take the expectation value of a plus a minus. Now a plus is the dagger of a minus, so I can see that what's going on is that I have two vectors. One of them is a minus acting on psi, and the other is the conjugate of a minus acting on psi. So if I define chi as a minus acting on psi, the right hand side here is simply the inner product of chi with itself. That's the length squared, the norm squared of chi, and that has to be positive semi-definite no matter what psi I begin with. It simply cannot be negative. Let's now apply this result to one of the eigenvectors of the number operator that we found previously. So let me call the eigenvalue c and the eigenvector also c, now labeled by the eigenvalue. So these are eigenvectors and eigenvalues of the number operator. So in such a state, if I take the expectation value of the number operator a plus a minus, then of course what is true is that I can simply pull out the eigenvalue and be left with the overlap of c with itself, which must be positive semi-definite, and so altogether it follows that c itself must be positive semi-definite. So the result of this is that one cannot keep going down the ladder forever, because no matter what value of lambda you started with, if you acted enough times with a minus, you will end up with a negative number. And what we've just learned is that n, the number operator, simply cannot have negative eigenvalues. So the spectrum of the number operator must terminate for some number of integer steps below lambda. Basically, those steps, you're only allowed to take as many steps that you still end up above 0. Now, the only way that process of generating lower and lower eigenvalues can terminate is that there comes a point at which you act with a minus on the last stage, the last step, which is I've labeled as lambda minus k, and when we act on that eigenvector we simply get 0. If we didn't get 0, we would end up with an eigenvector with a still lower eigenvalue. So that's really the only way for the process to terminate. Now the state lambda minus k also has the property that if I act on it with a plus times a minus, I must also get 0, since the a minus already gives 0. So that means it's also an eigenvector of the number operator with eigenvalue 0. Since lambda minus k is the eigenvalue for the number operator, it follows that lambda minus k is 0, or that the starting value of lambda was in fact exactly k, the number of steps it took me to get to the bottom of the spectrum. So then it's convenient to reorganize how we think about it and say that we have a lowest eigenvalue of the operator n, which is 0, and then from it we can construct a rising tower of states with 1, 2, 3, 4 and all positive integers as eigenvalues of the number operator, and all these states are reached by simply acting with a plus the appropriate number of times. Of course, starting at any state you can move down by using a minus. Okay, so we've identified the spectrum of n with the integers and 0, and so the Hamiltonian, which I remind you was h bar omega times the number operator plus a half, then has a spectrum which looks like n plus a half times h bar omega, where n is again 0 onwards, takes integer values. And the eigenvectors, as stated, are constructed by starting with the lowest eigenvector of the number operator, which is also the ground state of the Hamiltonian, and is also referred to as the vacuum of the creation and destruction operators of the ladder operators. So I start with this vacuum or ground state, act on it with an appropriate number of times with a plus or a dagger, and I get to the appropriate eigenstate of the Hamiltonian with this energy. The question is the ground state as properly normalized with respect to some inner product which we have on this space that we are working on. So while that is true, that doesn't guarantee that the form that I wrote earlier with a plus acting an integer number of times on the ground state is a state which is itself normalized. But I can compute its normalization by using the algebraic properties that we have figured out so far. So for example, consider the state a plus acting on the vacuum, and consider its norm squared. So that's a plus acting on the vacuum or the ground state and its conjugate, its Hermitian conjugate, which then can be written as just the expectation value of a minus times a plus. Now this is not the number operator, but I can turn that into the number operator by using the commutation relation, and when I do, the number operator acting on the vacuum is going to give me 0, or a minus is going to annihilate the vacuum. You start to see why we use these words the way we do, and we get that the expectation value simply reduces to the norm squared of the vacuum state, which is in fact 1. So in the context of quantum field theory, as a digression, the a dagger in A would be viewed as actually creating physical particles from the vacuum, not as an act of creation, but as the mathematical operators that relate the state of the universe with one particle present to the state of the universe with no particles present. Alright, end digression. So in the same fashion, I can work out the norm squared of more highly excited states. When I do this, basically writing strings of a minuses and a pluses and reshuffling them around till I can read off what the expectation value is, I get a very nice answer. The norm squared of a plus acting n times on the vacuum is simply n factorial. So in order to get a normalized state, which I'm going to call n, what I do is take my unnormalized eigenvector and divide it by the square root of n factorial. The same technology can be used to find expectation values of any polynomials in x and p. So for example, if you want to find the expectation value of x squared in the eigenstate n, you'll start by writing the operator x as an appropriate linear combination of a plus and a minus. I'm not putting in all the messy factors. And then when you work out the square of x, that will have terms like a plus squared, a minus squared, a plus a minus, and a minus a plus. Now the expectation value of a plus squared is going to be 0, because you'll start with an eigenstate n, act on it twice with a plus, you'll end up with something that's proportional to the eigenstate n plus 2, but that's going to have 0 overlap with the eigenstate n. Likewise with a minus squared. So the only time you're going to get something non-zero is when you have equal numbers of a plus and a minus, in this case a plus a minus and the term a minus a plus. And with a plus a minus, that's the number operator, so you can read off what that's doing. But with a minus a plus, you'll have to reshuffle it into the number operator by using the commutation relation, but that you can do. And when you're done with it, you'll be left with a number. So it's a mechanical procedure. It obviously will get somewhat tedious if you have, say, x to the 24th to calculate, but it simply can be done by this sort of reshuffling using the algebra and the definitions of the eigenstates that we have by now. In this fashion, we have by now this self-contained algebraic treatment of the spectrum of the harmonic oscillator, where we can really calculate anything we could calculate in the wave function approach. Nevertheless, as a final step, it's nice to connect to the wave function approach, and the way we do that is to find what wave function corresponds to the vacuum state in the algebraic approach. So the vacuum state or the ground state is defined by a minus acting on the vacuum gives me 0. And so if I translate a minus into the linear combination of position and momentum operators written in the wave function approach, I get a differential equation which says that h bar times d by dx plus m omega x acting on the wave function psi 0, the ground state wave function, has to give me 0. This is a first order differential equation which is easily solved, and lo and behold, the solution is the ground state that we found earlier. It's the Gaussian. To find the nth excited state of the harmonic oscillator in wave function language, I take my ground state and I construct again explicitly the differential operator that corresponds to a plus, raise it to the power n, which is to say I'm going to act on it n times repeatedly, and when I act on it in the Gaussian and go through now the relevant differentiation using the chain rule however many times I have to, I'm going to get a wave function which will agree with the wave function that I found earlier, and if I normalize everybody correctly, I will actually get the correctly normalized wave function. So we see in this fashion that the algebraic approach and the analytic approach are precisely equivalent.